Please join me in welcoming Tom to the stage.
Hello, everyone. How many of you have ever been in an eye tracking experiment or have used an eye tracker before? Maybe just show me, raise your hand. Okay, that will be an easy audience for me, I think. Eye tracking is about measuring features of the eye and characteristics of the eye. So it's about extracting information like the point of gaze and the eye position. We are using then these features to derive higher level information like the user's attention, emotions, and even cognitive workload. AR is almost as old as eye tracking itself, and it has the same crude beginnings. Both technologies were around for many, many decades, and it took many years of research and miniaturization of components to allow us to get to a point where we are right now. The hardware required for eye tracking is fairly simple. All you need is a single camera per eye and a little bit of illumination. All the rest of the magic happens in software. It might seem, eye tracking, if you look at it for the first time, it might seem as an easy problem to solve. If you do a quick Google search, you find many research papers about the topic, how to do a simple gaze tracker. The problem with that is that this will usually end up in a result which works just for you, or maybe your buddy in the lab. Making it work for everyone was the challenge me and my team had to face. And that's also where most of the work went into. The key component for every tracking and interaction technology is making it robust. If it doesn't work with everyone, and it doesn't do so always and reproducible, consumers will simply not accept it and will not use it. So after figuring out the technology, that's where the fun part really started at SMI. That's where we could use it to create a better user experience. And I want to talk to you today a little bit about how we can use eye tracking to help AR become ready for the masses. And one of the key components for that certainly is creating the perfect illusion for the user. The dream about head-mounted augmented reality is to create virtual objects which blend seamlessly with real objects. So essentially, we want users to not be able to tell if that's a virtual object or a real object. So, and the key component for getting the illusion right is knowing where the user's eyes are. Because the user's eyes are used in order to position virtual cameras, where then objects are rendered and then blended in our field of view. There are essentially two major depth cues which our eyes use, which is accommodation and vergence. There are other depth cues like occlusion and size of objects, but let's say these are the ones which are most relevant for optics. Current generation of head-mounted displays and wearable solutions have a fixed focus plane. So that means the light will always come out of a fixed distance, which is somewhere, like, it depends on the device, which is sometimes it's like a 2-meter range, sometimes it's projected to infinity. But what we do have also in current generation of devices is the vergence depth cue. It's essentially what our eyes are using that is to judge how far an object is apart. Because what we do is when we look at an object, we are trying to align the image with a spot in our retina called the fovea. And so what we do is if we look at a close object, we bend our eyes more together. If we look at a far object, the eyes are essentially parallel. So what we have to do in a virtual object is to create this effect as good as possible and to align it as good as possible with reality. And what we need to know for that is where the user's eyes are. Because if we would want to project a virtual object covering another object, let's say both in 1.5 meters distance, what our eyes will do is they will look at the real object and will bend in a certain proportion depending on the user. And then we have to make sure that we display the image for each eye exactly at the position to align with that point of view. So as you can easily imagine, we need to know where the eyes are for that. And if we get that wrong, and we assume a too large IPD, let's say if we have the user enter it and the user is just guessing about what my IPD is, what will happen if it's too large, that objects will appear closer and smaller than they're intended. So if we take the example again that we have a 1.5 meter object and we want to overlay something which is covering that object, then this overlay will kind of hover a little bit in front of it. And this will always feel weird and then breaks the illusion and disconnects us from the augmented reality. The same effect goes vice versa. So if we have a too small IPD, objects will appear farther and larger than they actually are intended. Another aspect about creating a perfect augmented reality interface is protecting a little bit the user. As you can easily imagine, as soon as we have the perfect illusion and we have the perfect augmented reality system connected to the internet or whatever will be, is that all of a sudden everything will battle for our attention. Everything will be augmented, everything will try to sell us something, get us in the store, will blink and pop up everywhere. And we can use eye tracking to help the user filter that, because this is what gaze is. Gaze is our perfect filter for attention. You can see that like if you have something called a cocktail party effect, where you have a lot of people speaking in the room, you look at a person and then you can listen to them better, right? This is how our ocular or ENT system is built. So what we can do with eye tracking is to help users not get swamped by augmented reality and by augmented objects, and help them to just give them information in their field of view where they're currently looking at, essentially give them information on demand. Another dream of augmented reality is to allow for hands-free interaction. A lot of the first applications will most likely be industrial applications, and they're currently already developed, as you can see in the show floor also here. And so in industrial applications, what you would want is you would want information while you're doing something. And this will most likely be something operating heavy machinery, being in gloves, working on some vaults or whatever. And so you can't just pull out your smartphone and look up the instruction manual of how do I have to turn it off or on. And this is where also eye tracking can help. And we have developed a showcase for that, which we SMI showed at AWE in Santa Clara, is where we prototyped a solution where we had a parcel service like UPS in mind, and where we allowed the driver to pick by vision. So there were like boxes which you can essentially select by looking at them, and then you would get context-sensitive information about the package. Is it heavy? Is it something you don't break? And then while getting it out, we know where the user's attention are, and then we can show him in a head-mounted display where to deliver it to, other information which he currently needs. So essentially, we give information when and where it's needed. Another neat implementation of that is if you know where the user is looking at, you know where the user's attention is, and you know with what objects the user would want to interact. So what we can do is also save computational load, which is still a big problem in augmented reality. We can just process an area where the user is currently looking at. So we can look at in these areas for objects which we might want to augment, might want to give information to. So essentially, eye tracking will help power consumer augmented reality solutions. One of the biggest topics, and probably what will pay for the integration for that, is this automatic display calibration. What we talked about earlier is that when you have a system which automatically knows where your eyes are. In current system, this is a manual step which takes between 1 or 5 minutes, and it has to be done every time you put on the headset or take it off. Another big achievement will be helping to give users information on demand when and exactly where they need it. And my personal favorite is offloading computational time from the system and using eye tracking to just process the image and process information where the user is currently paying attention to and where the user is most likely to interact with. I hope I could give you a little bit of an introduction to how eye tracking is used in augmented reality, and I'm happy to take some questions now.
here if you want to use them.
Are you relating any of the eye tracking to emotions? And how does that play into adapting systems and applications?
Well, eye tracking gives you many, many features of the eye. One is also you get pupil diameter, and emotional responses is tightly coupled with pupil dilation. So eye tracking can be used for that. So we can create essentially attentional interfaces which are user-aware and can use the user's emotions for that. It's still a little bit challenging, as the key component for that is, like I said, the pupil dilation. And you will have to be carefully filter out environmental conditions like, I don't know, brightness increases or decreases in order to really have a good signal-to-noise ratio, so to speak. But yeah, it's possible. There are many people doing research in that, so are we looking into that. But it will take a little bit to get it robust. But essentially it works. In a controlled environment, it works perfectly. Or almost perfect.
So you were can you hear me? Yes. You were saying that you can avoid automatic display calibration.
So we can avoid a manual display calibration.
But for eye tracking, I think you need to do a calibration for the eye tracking or not.
Exactly, but this will be, so essentially the eye tracking technology me and my team have been working on requires a one-time user calibration. So it's like unboxing your iPhone, making it learn your fingerprint, and then you do that one time. And then because we do a 3D reconstruction of all eye features, it's a one-time thing and you don't have to ever do it again.
The other question, what is the angular accuracy of the eye tracking?
So this depends on the system and then the optical setup, yada, yada. But it's roughly around 0.5 degrees over the whole field of view, which is half your thumb on arm's length.
Thank you.
Anyone else? Okay, then thank you very much for your attention. Thank you.